Hello everyone, I'm Dan Fullerton, and in this video we're going to take a look at the 2018 AP Physics C Electricity and Magnetism Free Response questions. Now as I begin this, just a forewarning, they have not yet released the scoring guide for these questions. So this is my first pass attempt at taking on these questions, and odds are pretty high that I make a mistake or two as we go through here, but hopefully we at least give you an idea of how you might go about tackling these questions, even if I happen to nuts up a detail or two. So with that, let's dive right in. Question 1. We have a charged plastic sphere surrounded by a conducting spherical shell. And in part 1, it gives us the volume charge function. Volume charge density function is a function of radius for the plastic sphere. And it asks us to consider a Gaussian sphere of radius r concentric with the plastic sphere. Means that plastic sphere and the Gaussian sphere have the same center. And we're finding an expression for the charge enclosed by the Gaussian sphere for the following regions. So it's not even having us do the full Gauss's law yet. We're just finding the charge enclosed. So for part A1, here where we're looking with a radius of less than a, I would look at that as our enclosed charge is going to be the integral of rho dv, which in this case, that'll be the integral from our initial radius r equals 0 all the way to some final value of radius r, which is going to be less than a. And in that region, the volume charge density is given by beta r. That's given in the problem. And then we also have our differential of volume. And what I'm going to look at there is I'm going to take the area of a sphere, 4 pi r squared, and integrate over some little tiny bit of thickness, of change in radius, dr. If we imagine taking that whole thing, flattening it out, and giving it some thickness dr. So our little bit of volume is going to be 4 pi r squared, the surface area of a sphere, times just that little bit of thickness, infinitesimally small bit of thickness dr. So now it becomes an exercise in a little bit of calculus. We could pull out our constants there. It looks like that'll be 4 pi beta. Oops, not implies that. That implies that Q enclosed equals 4 pi times beta integral from r equals 0 to final value r. Looks like we've got an r cubed dr. All right, which implies then that Q enclosed equals 4 pi times beta. Integral of r cubed is r to the 4th over 4. Evaluated from 0 to r just works out to be pi beta r to the 4th. So there's 1a part 1, and 1a part 2 says now we're going to do this for r between a and b. And in that case, between a and b, all the enclosed charge is still just at a. So anything between radius a and b doesn't add any extra charge to it. So if this is our answer for 1, for part 2, our charge enclosed is just going to be the same thing, but instead of r, all we have to do is put our radius a, because that's the maximum radius of our plastic sphere. That's just going to be pi beta a to the 4th. And I think that covers us there for 1a. Now for part 1b, we're going to go a little bit further. We're going to use Gauss's law to find the electric field. And in a helpful manner, we've already found the enclosed charge. So for part B1, Gauss's law, the integral over the closed surface of E dot dA is equal to our total enclosed charge divided by epsilon 0. Which in this case, our total enclosed charge, we already figured out in that region, was pi beta r to the 4th over epsilon naught. This implies then, on the left-hand side, because we chose our Gaussian sphere carefully, the electric field is a constant everywhere due to that spherical symmetry. So E integral of dA is just going to be that area. So we have the electric field times the area, 4 pi r squared, the area of our Gaussian sphere, must equal pi beta r to the 4th over epsilon naught. A little bit more algebra. Electric field then equals beta r squared over 4 epsilon naught. Very good. And for B2, doing the same basic thing, except now we are doing it in the region between A and B. And again, we've already calculated the enclosed charge. So I'll start with Gauss's law again. Integral over the closed surface of E dot dA is our total enclosed charge, the charge enclosed by our Gaussian surface, divided by epsilon naught. Again, left-hand side, electric field times the surface area of our Gaussian sphere, 4 pi r squared, is equal to our total enclosed charge, which now is pi beta a to the 4th over epsilon naught. Same algebra again gets us to beta, implies then that our electric field is equal to beta a to the 4th, all divided by 4 epsilon naught r squared. And I think that covers us pretty well for 1b. Moving on to 1c. 1c, at any point outside the conducting shell, it's observed that the magnitude of the electric field is 0. Well, in that case, we know that the total enclosed charge must be 0 by Gauss's law. So C1 says determine the charge on the inner surface of the conducting shell. All right, well, for part C1, we know that the integral over the closed surface of E dot dA, Gauss's law, equals total enclosed charge over epsilon naught. Inside a conductor, we know the electric field equals 0 in our electrostatic conditions, which implies then that the total charge on that inner surface plus the charge on our plastic sphere has to be 0. Therefore, our charge on that inner surface must be equal to the opposite of the charge in our plastic sphere. Therefore, our inner charge on the inner surface of that conducting spherical shell must be equal to minus pi beta a to the 4th. And then C2, determine the charge on the outer surface of the conducting shell. So for C2, Gauss's law again, integral over the closed surface of E dot dA equals Q enclosed over epsilon naught. All right, left-hand side is going to be the electric field times the area of our Gaussian sphere again, just like we did previously, must equal the total enclosed charge. And if we know that the electric field out there is 0, that means that Q enclosed over epsilon naught must be equal to 0, which means the electric field must be equal to 0. Therefore, Q enclosed must be equal to 0. Now, for Q enclosed to be equal to 0, that means that the charge on the outer surface of our conducting shell plus the charge on the inner surface of our conducting shell plus the charge in our plastic sphere must sum up to 0. Well, we've already figured out that Q inner is minus beta pi a to the 4th. Did that right up there. And Q plastic, in our plastic sphere, our enclosed charge is beta pi a to the 4th. Therefore, all that leaves when we substitute in is that Q outer must be equal to 0. And I think we're pretty well covered now for 1C. Part 1D, Section 1, wants us to sketch the electric field as a function of distance r from the center of the sphere. All right, we've already figured out what the electric field is, so now we're just graphing it. Looks to me like we start here at 0. At point A, we're going to come up to a maximum, as this is related to beta r squared over 4 epsilon naught. And from there, we're going to come down something like that. And here we're going to have a discontinuity in the metal itself, no electric field, but because we've got charge on the inner surface, we can have a discontinuity. And in this region, we calculated beta a to the fourth over 4 epsilon naught r squared. So maybe not my prettiest hand-drawn graph, but I think you get the idea of what the electric field would look like in that region. D2, what we're looking at is 4 points. We've got our plastic sphere here, point W. On the outer surface of it, we've got point X. Around that, the inner surface of our conducting sphere, point Y. And outer surface, we've got point Z. And it wants us to rank the electric potential, W, X, Y, and Z. And the way I think about this, as far as figuring the potential, is thinking about the work done in order to move a charge from infinity to those points. There's no electric field outside this. We already proved that. It was given in the problem. So taking a positive charge from infinity and moving it to Z requires no work. So that's got to be our minimum. And Y and Z are both in a conductor, no electric field, constant potential, so that has to be 3. Moving closer to X, now we're working against that electric field in that region to move that, so we're doing work on the charge, higher potential, and to go right to the center, we still have to do more work in there. So I would do it something like that, taking that positive charge from infinity and trying to move it to that spot, figuring out where we're doing the work, and therefore figuring out the potential at those different points. All right, moving on to question number 2. Looks like we now have our circuit capacitor question here. And this is a lot like a lab we typically do in our class. We've got some aluminum foil on both sides of a stack of paper. It tells us the area of the paper. And what we're going to do is we're going to keep using different amounts of paper, changing the thickness of our dielectric and measuring the capacitance. And first thing it asks us is what we would want to graph in order to find a straight line that we could use for a numerical value for the dielectric constant of the paper. Well, I would start by recognizing capacitance is going to be equal to our dielectric constant kappa, epsilon naught, A over D for a parallel plate capacitor. Therefore, kappa is equal to capacitance times our thickness divided by epsilon naught A. So if we wanted to do that, we're going to have to look at that as slope over epsilon naught A, a couple constants in this problem. So what I would probably put on the horizontal axis to do this is going to be 1 over the distance. Since we've got distance up there, rise over 1, we'll have 1 over distance in the denominator to put D up there. And on the y-axis, the vertical, we'll just plot our capacitance. It gives us a table then and says, using the table, figure out what we would want to plot, what different values we would put in there. Well, on my x, the horizontal, I would put 1 over our thickness, our distance, so that's going to be 1 over meters, and that's just 1 over whatever this value is in the calculator. That's going to be 22.2, 27.8, 37, 55.6, and 100. And for capacitance on our y-axis, this is 6.5 times 10 to the minus 11. That's a little awkward there. Why don't we do capacitance in picofarads times 10 to the minus 12? So that'll be 65, 74, 89, 119, and 210. Something kind of like that. So we've labeled each column, we've given them units. I think we're okay to go on to 2b. In 2b, we are now going to plot the data. Yeah, we really like these plot problems where we use a slope in order to find some physical value. So on the y-axis, we've got our capacitance in picofarads, and on the x-axis, we'll have 1 over distance in 1 over meters. And along the y-axis, looks like we could go 0, 50, 100, 150, 200, 250, And along the x-axis, 20, 40, 60, 80, 100 will cover us for the different values that we have here. Now it comes to plotting points, and I'm not going to make you sit around while I plot these points, but when I did my graph, they all lined up something kind of like this. I think we had one way over here. At that point, you're going to use a straight line, draw your best fit line. Doesn't have to go through the points, but hopefully about the same distance of points above and below. Maybe something kind of like that. Just doing this fairly quickly. And then for 2C, using that straight line, find the dielectric constant of the paper. Well, we determined that our dielectric constant kappa was going to be slope over epsilon naught A, because our slope was rise over run. Rise was our capacitance over run. Epsilon naught A, 1 over D is our run, so that works out to CD over epsilon naught A, which is what we had previously. So slope over epsilon naught A. Our slope. Pick 2 points on your graph. Try and find points on the line, not specifically data points. Based on your graph and where things fall, try and pick points that are pretty easy to figure out exactly what those values are. Those might be 2 points as an example, depending on your particular graph and where you put those points. But that would then be y2, oh, we can't see that color very well, y2 minus y1 over x2 minus x1. Fill those in with units, calculate what you have, and I came up with something right around 1.91 times 10 to the minus 12 farad meters. Kappa then is slope over epsilon naught A, which would be 1.91 times 10 to the minus 12 farad meters divided by epsilon naught, 8.854 times 10 to the minus 12 coulomb squared per Newton meter squared, times our area, 0.06 square meters. Put all that in, and I come up with the kappa of about 3.60. And kappa, that dielectric constant, is unitless. So hopefully something kind of close to that, somewhere in that ballpark. So I think that covers us for part C. Part D looks almost like a whole new problem. They're saying that it's the same capacitor, but I don't think it really matters. A circuits question with capacitors now. Okay, looking at this one. Calculate the current in the battery immediately after the switch is closed. Well, immediately after the switch is closed, that capacitor is going to act like a wire. So the first thing I'm going to do is I'm going to redraw my circuit for the situation immediately after that switch is closed. Make it a little simpler. So we've got 36 volts. Our switch is closed. I have two 80 ohm resistors in parallel. The equivalent resistance for those two is 40 ohms. R1, R2 over R1 plus R2. Our capacitor is acting like a wire. I don't have to worry about it. Immediately after the switch is closed, we have another 80 ohm resistor, and we come back to our battery. So to my mind, that's our equivalent circuit. Find the current in the battery. Well, series circuit in our equivalent circuit, which means the current is the same everywhere in the circuit, that current is going to be equal to our potential difference divided by our equivalent resistance, which is 36 volts over 120 ohms, or about 0.3 amperes. So there's 2D. 2E says find the time constant for this circuit. In an RC circuit, the time constant is RC, where R is our equivalent resistance in this configuration, which is 120 ohms, 80 and 40 in series, again, only right after the circuit is closed, while that capacitor is acting like a wire. And the capacitance is 18 nanofarads, or 18 times 10 to the minus 9 farads, gives me a time constant of 2.16 microseconds. That didn't seem too bad either. And part F in two sections. F1, A and B measure the time it takes after the switch is closed for the voltage across the capacitor to reach half its maximum value and find it is longer than expected. Student A assumes the capacitance value is correct. would student A conclude that the resistance value is larger or smaller? Well, what they find is that the time is longer than expected. So what do they think about R? I would say that R is larger than measured. And something that would lead to that, what could make you assume this or account for this experimentally? Well, we treated this as an ideal battery. If that battery had some extra resistance, then we would actually have a larger R than measured. So I would say something like R internal for the battery exists. It's not an ideal battery, it's a real battery. That would explain what's going on there. For F part 2, student B assumes the resistance value is correct. Would student B conclude the capacitance value is larger or smaller than measured? Again, if tau equals RC, we've got a longer tau, and we are figuring that R is correct, then capacitance has to be higher. So C is larger than measured. And what could account for that? A couple different ways you could answer it, but to my mind, the simplest would be that the paper thickness, we're assuming that that is just one sheet of paper, which is a mighty small measurement to extrapolate from doing 500, 400, 300 sheets. So I'd guess that the paper thickness is smaller than average. C equals kappa epsilon naught A over D. If that thickness of the paper is a little bit smaller than we measured, then we're going to have a higher capacitance. So something about thickness of paper is smaller than we'd calculated or anticipated. And on to number 3. All right, our electromagnetism question. This one takes a little bit of three-dimensional thinking and reasoning. When I first saw this question, I looked at it for a while and tried to visualize it and redrew it several ways, trying to get a good feel for what they're really talking about here. It takes a little while to read this one and come up with a 3D model in your mind. It's worth taking a minute or two before diving into the questions. Now for part A, it says use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. All right, so an Ampere's law question. For 3A, Ampere's law, integral over the closed loop of B dot dl equals mu naught times the current that penetrates our Amperian loop. All right, so we've chosen our Amperian loop such that we will have a uniform magnetic field everywhere by making it concentric around the wire. So in our case, because of how we chose that loop, B has to be a constant. So B comes out of the integral sign. Integral over the closed loop around a circular loop around that wire is just going to be its circumference, which in our case would be 2 pi d. And that has to equal mu naught times I penetrating, and the current that penetrates that loop is just I. Therefore, our magnetic field strength in there is mu naught I over 2 pi d, magnitude of our magnetic field strength due to wire 1. Part B, derive an expression for the magnitude of the net magnetic field at point P. All right, looking at point P, here's where we get into some of that two-dimensional thinking. The magnetic field due to that first wire we just found as mu naught I over 2 pi d, and I'm just going to call that B for now in order to keep this nice and simple. For the second wire, we have twice the current, but it's at that same distance, so it's going to have a magnetic field strength of 2 mu naught I over 2 pi d, or 2b. And these, as we look at the right-hand rules and directions, are going to be perpendicular to each other. So if we wanted to find the net of those is going to be the square root of b1 squared plus b2 squared, which will be the square root of b squared plus b2 is 2b. 2b squared will be 4b squared, or square root of 5 times b. And again, if b is mu naught I over 2 pi d, this becomes a mu naught I square root of 5 over 2 pi d. So that's how I would do part B. Moving on to part C of this problem. Calculate the numerical value of the angle to the horizontal for the direction of the net magnetic field at point P. All right, looking at this one again, this is going to take a little bit of interpretation and three-dimensional thinking as we try and figure out horizontal when we've got these different views. And the way I drew it and thought about it was, here we have our wire 2 with the current going this way from figure 1. Due to that, over here at point P, this B2 is going to give wire 2 is going to give a magnetic field into the plane of the page over at point P due to the right-hand rule. Due to wire 1, which is coming out of the page toward us, we're going to get a magnetic field that way. So that's due to B1. So if I were to draw this, if I try and take this, and instead of looking at it straight on, I'm going to pretend I'm pulling myself over to the right and looking at it this direction. What I'm going to see, the way I would visualize that, is it looks to me like I've got B2, which has a magnitude of 2B in that direction, and up I've got just B, the value of B1. So what I'm doing is into the plane of the page is this direction now, and I'm looking at it from this right side, looking at it to the left. I've still got B1 up. So my net magnetic field is basically in that direction, where I'm going to call that our angle theta. If I look at it from that perspective then, theta is the inverse tangent of our opposite over our adjacent of B over 2B, which is the inverse tangent of 0.5, or about 26.6 degrees above the horizontal. All right, looking at part 3D, which I think is one of the trickiest questions on the test, if not, I'd say without a doubt, the trickiest questions on the test. It says wire 1's now released. Ignore gravity. What describes the initial motion of wire 1 due to the magnetic field of wire 2? And if I look at that first diagram in figure 1, the magnetic field from wire 2 is going to be in the opposite direction as the current in wire 1. So those are going to be anti-parallel. You're not going to see any magnetic force on wire 1. The magnetic force magnitude of it is QVB sine theta. If theta is 180 degrees, the magnetic field and current are in opposite directions, no force. But if you go over and you look at figure 2, we have to realize we're not looking just at where they cross. We have to look at the entire wire. So looking at it from the perspective of figure 2, there we have the current from wire 2, which is going to create, at the top, we're going to have a magnetic field due to wire 2 into the plane of the page, and down below it, it's going to be out of the plane of the page. Now, with wire 1 having current going in this direction, there's our current. I take a look at the magnetic force on that wire, and we have positive charge flowing down, the magnetic field out, V cross B, or the magnetic force is going to create a force that direction on this side of the wire. And up here, from figure 2's perspective on wire 1, we have charge moving this way, positive charge, magnetic field into the plane of the page is going to create a force that way. So what I think we're going to see here for part D is we're going to see that wire 1 will rotate clockwise as viewed in figure 2. So we really have to look at it from perspective of both figures and look at the ends of the wire, not just right where the two cross. But I think you're going to see a clockwise rotation as viewed in figure 2. Okay, now we've got a rectangular loop up above wire 2. Tells us what the current in wire 2 is as a function of time. And what we're looking for is finding the flux as a function of time. So when I look at this one, we have wire 2 with the current traveling this way, and up here we've got our loop. At some distance, d over here, and we've got some width, w, so this is d plus w as we head in this direction. if I wanted to find the entire flux, knowing that it depends on where we are in time, what I'm going to do is I'm going to break this up into little tiny slivers, each with some small thickness, dr, as we go from d to d plus w. So I would look at this and say that our magnetic flux through that loop is going to be the integral of B dot dA, which is going to be the integral, or pardon me, just integral B dot dA, which is going to be the integral from R equals D to R equals D plus W of our magnetic field strength as a function of time, magnetic field strength times our length times dr to give us our dA. So LdR, which implies then that our flux is going to be the integral from D to D plus W of, well, our magnetic field is going to be, what do we have here? B of t mu naught over 2 pi r times B of t, which is 2 I naught times 1 minus kt, magnetic field due to a wire, mu naught I over 2 pi r, times L dr. Looks a little scary, but really a lot of that's constants. And it's not even going to have us integrate it. We've just got to find the form that matches that. And as I look at my different choices, mu naught 2 I naught over 2 pi r 1 minus kt. This looks to me like we're in the bottom left. And what the bottom left one says specifically is flux from r equals d to r equals d plus w of mu naught times 2 I naught over 1 minus kt all over 2 pi r L dr. So just a slight rearrangement to get the form that they have in the bottom left choice. So that to me looks like our favorite answer. Part F and G. F, given that the flux through the loop as a function of time is given by that equation, so they've actually calculated it for us, find an expression for the current induced in the loop. Well, the current induced in the loop is going to be the EMF divided by the resistance. So if we figure out the EMF, we're almost done. The EMF, Faraday's law, is minus d phi b dt, opposite of the time differential of the magnetic flux, which is the opposite of the derivative with respect to time of what they just gave us for our function. We have mu naught I naught L times 1 minus kt over pi times the log, natural log, of d plus w divided by d. That looks a little scary, but notice this log is a constant, mu naught I naught L over pi, all constants. Our only variable in there is that t. So that's not nearly as bad as it looks if we pull out the constants. So I would say that that is minus mu naught I naught L, all divided by pi, natural log of d plus w divided by d times our differential of 1 minus kt. Differential of 1 minus kt is just going to be minus k. Negative, negative will cancel out, and I come up with mu naught I naught L k over pi times the natural log of d plus w divided by d. So, oops, I got to be careful there. Might have gone a little fast. There's our EMF. It wants the induced current. So to find the induced current, well, induced current is just our EMF divided by the resistance. So that's going to be mu naught I naught L k over pi log, natural log d plus w over d divided by our resistance. So it looks to me there like we've answered that question, our induced current. And for part G, what is the direction of the current, if any, induced in the loop as seen in figure 3? Our Lenz's law question, of course. and justify your answer. Well, as I look at that equation for the flux, I see that as time increases, the flux into the plane of the page decreases. The induced current always opposes that change by creating a magnetic field into the page, which corresponds to a clockwise current consistent with Lenz's law. So, not consistent, clockwise would be my answer, and the justification would be what we just said there as we walk through Lenz's law. Don't just write Lenz's law or the right-hand rule. Talk about how as time increases, the flux into the plane of the page decreases, and that induced current opposing that change, which corresponds to a clockwise current induced in that rectangular loop of wire. And that concludes the 2018 AP Physics C E&M free response questions. Thanks so much for your time, everybody, and make it a fantastic day.